Welcome, my fellow explorers and lovers of science. Today, I invite you to join me on a fascinating journey not just to see gold, but to understand how it can be carefully, patiently, and intelligently extracted from complex rocks that hold not only gold, but other valuable metals like iridium, cobalt, and nickel. We're not going to use cyanide, mercury, or any other harmful or dangerous shortcuts. Instead, we'll rely on solid chemistry, real lab work, and safe materials. This is not just about gold, it's about learning, experimenting, and mastering the process. You see, many rocks found in nature, especially black sands, volcanic materials, or veins, contain a complex mix of metals. While most people think only of gold, they often overlook hidden treasures like iridium, one of the rarest elements on Earth, or cobalt and nickel, essential for modern batteries and electronics. In this detailed, step-by-step experiment, I'll guide you through every phase, from crushing the raw rock into powder, separating the heavy minerals using gravity, roasting the concentrate to prepare it for chemical treatment, and then dissolving away the unwanted metals to isolate gold and iridium. You'll see everything, hear my reasoning at each step, and understand why we do what we do, not just how. Whether you're a hobbyist, a student, or simply curious about how metals are separated in real life, you'll find value here. So grab your notebook, maybe even your own sample of rock, and follow along. By the end of this video, you won't just witness the recovery of gold, you'll understand the science behind it. Let's begin. This is the type of rock we'll be working on today. At first glance, it might look like an ordinary piece of stone, dark, rough, and heavy, but if you look closer, you'll notice some unusual features: its weight, its metallic shine in certain areas, and the presence of fine grains that suggest it's much more than just a rock. This specimen is what we call a polymetallic, or a rock that contains multiple valuable metals locked inside. Through experience, testing, and visual inspection, we can tell that it's rich in several heavy metals, most notably gold, iridium, cobalt, and nickel. Each of these elements has unique properties, and they all behave differently under heat, acid, and physical separation processes. Gold, for instance, is soft, malleable, and dense. It's often found in its native metallic form. Iridium, on the other hand, is one of the densest and most corrosion-resistant elements known to man. Cobalt and nickel are lighter but still valuable, often found as sulfides or oxides mixed into the mineral matrix. But before we think about extracting anything, we need to take a crucial first step. We need to break the rock down physically and mentally. Physically, we'll crush and grind it into a fine powder so the individual particles of metal are freed from the surrounding material. Mentally, we need to understand what we're dealing with, the structure, the composition, and how these elements are bonded within the rock. Only when we understand the material can we choose the right methods to separate each metal carefully and efficiently. So let's get started with that first and very important phase, breaking the rock down to unlock its hidden treasures. Our first step in this journey of extraction is a very physical and essential one: crushing the rock into a fine, consistent powder. This may seem like a simple mechanical task, but it's actually one of the most important steps in the entire process. Why? Because within this rock, the valuable metals gold, iridium, cobalt, and nickel are not sitting loosely on the surface. They're locked tightly inside a dense, complex matrix of minerals, like tiny prisoners trapped within stone. In order to free them, we must reduce the rock into particles small enough to allow gravity, chemicals, and heat to interact directly with the metal content. We start by using a hammer or a mechanical jaw crusher to break the larger chunks into smaller gravel-sized pieces. Then we continue refining it with a ball mill, a grinder, or even a hand mortar and pestle until the material becomes as fine as sand or even finer. The finer the powder, the better our chances of separating and recovering the metals efficiently in the later steps. It's all about increasing surface area and exposing every hidden fragment of gold or iridium to the processes that follow. This stage also gives us our first physical connection with the ore. As you crush, you'll feel the resistance of the rock, hear the difference in texture, and begin to notice small changes in color or density that hint at the presence of metals. It's dusty, it's noisy, and it can be tiring, but it's absolutely necessary. This is where our real work begins. From this powder, we will rebuild value, step by step. We'll now move on to the next critical phase of our process, gravity separation. This technique is based on one of the oldest and most reliable principles in mineral extraction: density. Every material has a specific density, or what we commonly call heaviness. Gold and iridium are among the heaviest natural elements known to man. When compared to the lighter minerals that make up most of the rock like quartz, feldspar, or clay, the difference in weight is dramatic. And that difference is exactly what we'll use to our advantage. In this step, we'll use water as a medium and tools like a gold pan, a sluice, or even a shaking table to separate the heavier particles from the lighter waste. As we agitate the powdered ore in water, the lighter materials will stay suspended or float away, while the heavier particles, our precious metals, will sink quickly and settle at the bottom. This is where your focus and patience matter most. You must observe the way the particles move. You'll start to notice that the black sands and dense spakes settle differently. They resist the flow, they cling to the bottom, and they sparkle under the light. Those are your indicators: gold, iridium, and possibly platinum group minerals. What we're doing here is called concentration. We're concentrating the most valuable elements into a smaller amount of material that we'll treat chemically in the next steps. It's like picking the ripest fruits from a large tree, leaving behind the leaves and stems. The more carefully we do this, the purer our final result will be. So take your time, control the water flow, and pay close attention. Nature is giving us clues, you just have to know how to read them. Now that we've concentrated the heavy minerals using gravity, it's time to move to a more advanced and transformative step: roasting. This is the phase where we take our collected concentrate, now rich in gold, iridium, and possibly sulfide compounds of cobalt and nickel, and subject it to high heat. But why do we do this? Many of the metals we want to separate, especially cobalt and nickel, are not present as pure metal, but rather as sulfide minerals. That means they are chemically bonded with sulfur in solid form, creating stubborn compounds that are difficult to dissolve or separate directly. Roasting is how we begin to break those bonds. By carefully heating the concentrate in open air, usually on a metal plate or inside a crucible, we allow oxygen to react with the sulfur, creating sulfur dioxide gas and leaving behind metal oxides or even free metal particles. The material will slowly change color as the chemical structure transforms, often from a dark, oily black to a reddish or gray tone. This step must be done slowly and safely. The temperature needs to be high enough, typically above 500 degrees Celsius, but not so hot that we risk melting the valuable metals or releasing harmful fumes too quickly. You'll want good ventilation or an outdoor workspace, and safety equipment like gloves and eye protection is absolutely necessary. You may notice a faint smell like burning matches, that sulfur dioxide being released. That's a sign the roasting is working. As the sulfur burns off, we're freeing cobalt and nickel for the next step, where they'll be dissolved using acid, while gold and iridium remain solid and unaffected by this roasting process. Roasting is both a physical and chemical shift, turning our raw mineral material into something more reactive, more accessible, and more ready for precise separation. In a way, we are unlocking the second layer of the ore's secret, and the results will show in the next phase, acid leaching. In the previous video, we explored how the stones are crushed, screened, and then roasted step by step. If you missed that important phase, don't worry. You'll find the link in the description box below. And before we dive into today's episode, if you haven't subscribed yet, make sure to hit that subscribe button and turn on the notification bell so you don't miss any of our upcoming content. And don't forget to like the video to help us reach more people who are passionate about this subject. Warning: this process is hazardous. Always wear safety goggles, protective gloves, respiratory mask, and work outdoors or under a fume hood. Your safety comes first. After roasting, we first wash the concentrate thoroughly to remove some impurities that may be present in the roasted material. This step helps improve the effectiveness of the following processes, such as acid leaching, by eliminating any unwanted materials that might affect the quality of the final result. Now that our concentrate has been properly roasted, we've prepared it for the next critical phase, acid leaching. Leaching is a process where we use a carefully chosen acid solution to dissolve specific metals from the roasted material, separating them from the ones that remain solid. It's like asking certain metals to leave the mix and go into the liquid while others stay behind. At this stage, our goal is to remove cobalt and nickel, which have now been oxidized during roasting and are more easily dissolved. For this purpose, we'll typically use a diluted solution of hydrochloric acid or sulfuric acid. These acids are strong enough to react with the metal oxides, forming soluble metal salts that move into the solution, leaving the gold and iridium untouched, still in solid form. We add water, and by slowly adding the acid to our roasted powder, here I used sulfuric acid, which we place in a glass beaker or acid-safe container. As the acid touches the material, a reaction begins. You might see a light bubbling or smell a sharp acidic vapor. This is a sign that the acid is reacting with the oxides of cobalt and nickel. It's important to stir the mixture gently and give it time, often several hours, to allow complete leaching. During this time, the solution will gradually change color, usually turning greenish or bluish depending on the concentration of nickel and cobalt in the mix. What's fascinating here is that this process is very selective. Gold and iridium, due to their chemical stability and resistance, do not dissolve in these simple acids. They remain at the bottom of the container, safe and separated from the other metals now dissolved in the liquid. Once the reaction is complete, we filter the mixture using filter paper or a fine mesh. The liquid contains our dissolved base metals, cobalt and nickel salts. The solid residue that remains is what we care most about next. It contains gold, iridium, and possibly other noble metals, now free from the bulk of the interfering material. Acid leaching is a key moment in our experiment. It's here where we really start to purify, removing the unnecessary and focusing in on the rare and the precious. With patience and careful handling, we are one step closer to isolating pure gold and iridium. Have you ever wondered how metals are melted and extracted at temperatures exceeding 2,400 degrees Celsius? That kind of extreme heat isn't something you can reach with an ordinary furnace. It requires a special industrial-grade one, far beyond the reach of most of us. Since I don't have access to such a powerful furnace myself, I turned to a friend who owns one of the rarest high-temperature furnaces in this field. He kindly agreed to help me out, but unfortunately, we weren't allowed to film inside the workshop due to strict privacy rules and safety regulations. But don't worry, you'll still get to see the result. I'll be showing you the final product after it's gone through the intense heat and rigorous process. A rare and valuable piece that's definitely worth the wait. Can you guess what kind of metal withstood 2,400 degrees Celsius and emerged from the fire in all its glory, Drop your guesses in the comments below. After separating the precipitate from sulfuric acid through filtration, the product is carefully washed several times with distilled water to eliminate any residual acid. This process is conducted under controlled conditions to avoid secondary reactions or alterations to the final compound, ensuring the purity and chemical stability of the sample. Iridium processing. Iridium is considered one of the rarest and hardest metallic elements known on Earth. It is highly resistant to heat and corrosion, which makes it difficult to melt and process using conventional methods. It does not melt easily, even when exposed to extremely high temperatures. To collect or purify it, special furnaces are required capable of generating very high temperatures exceeding 2,400 degrees Celsius. This temperature is sufficient to melt this stubborn metal. It is recommended to use plasma furnaces or electric arc furnaces for this purpose, as they can produce concentrated and efficient heat. After melting, the metal can be cooled and collected as solid pure ingots, or converted into fine metallic powder used in precision industries. It may also be sold directly in its raw purified form, provided that its purity is verified and it is completely separated from accompanying impurities and other metals like ruthenium or palladium. Iridium is used in advanced applications such as manufacturing aircraft spark plugs, surgical tools, and microelectronics due to its unique properties. The method used was as follows. First, the gold was melted at a temperature of 1,100 degrees Celsius, then poured into a mold, completing the melting process. This led to the separation of gold from iridium due to the difference in melting points and density. Thanks for watching.